Welcome to this air management system guide. The air management system has been designed to automatically reduce the air consumption of your machine when it's powered but not running. For example, when your machine has stopped production during break time, over the weekend, during a shift, tool or parts change. You could still be consuming air from air purge equipment, worn seals and leaking pipe connections. The air management system works on the principle that by reducing the supply pressure, the air consumption also reduces. So, how does it work? Here we have a typical air management system assembly which is made up of three main components. The first component is the standby regulator, which can be a manual or electro-pneumatic type. In this instance, we can see the electro-pneumatic type. Either option can be used to control the machine supply pressure. Next is the air management hub. This monitors the airflow, pressure, temperature of the air, and, if required, can provide an external communication directly via an OPC-UA connection, Ethernet IP, Profinet or EtherCAT. The final component is the residual pressure release valve. This can be used to isolate and vent the air supply downstream of the air management system if required. In some cases, you may decide that the machine's supply pressure cannot be switched off completely when the machine is only idle for a short period of time. If the machine is exhausted of air, the air management system will also control the speed at which the pressure is reintroduced. This is commonly described as the pressure ramp-up or soft start function. The air management system has three function modes. Operation mode. This is when your machine is working normally as if the air management system were not fitted at all. Standby mode controls the air at a lower pressure for when your production has stopped and the machine is in an idle condition, as described earlier. And finally, isolation mode, which allows you to isolate and exhaust the downstream pressure if you want to. The air management system needs to be configured with your specific machine requirements, such as the expected standby flow rate and the lowest practical standby pressure required for the machine need to be set within the unit. In addition, a signal to initiate the standby function should be received by the air management system. This can be provided remotely via a network communication signal or alternatively a directly wired 24-volt DC digital input or logic high from a contact on the machine, such as a PLC output or relay. This method is demonstrated later in this video. When your machine is in operation mode, the pressure and flow rate is as it would be for normal production running purposes. When the machine air consumption reduces below the predefined threshold flow rate, the standby on delay timer is started. Any time duration settings can be decided by you. Once the delay timer has expired, the air management system is then waiting for a 24-volt DC standby signal from the machine to be received. This will trigger the air management system to revert to the predetermined reduced standby pressure. Any leaks, open nozzles or air purge will consume less air due to the reduced pressure. If the air management system remains in standby mode longer than the isolation delay time period, again decided by you, the air management system can close and exhaust the supply of air via the residual pressure relief valve, reducing leaks and air wastage even further. When the standby signal is removed, the air management system goes back to its operation mode and increases pressure back to normal levels. We will now demonstrate the air management system functions with a practical example. Currently, the machine, simulated here by a cylinder in continued operation, is in operation mode and the average flow rate is approximately 180 litres per minute and the supply pressure is 5 bar. Here we've simulated a leak somewhere on the machine by the addition of a flow controller below the actuator. So the consumption here is the actuator move-in and the continued air loss from the flow controller or leak. In this demonstration, the standby flow rate threshold has been set to 100 litres per minute. So if the flow drops below 100 litres a minute, the machine is considered idle and only the leakage flow is present. The flow from the leak is approximately 78 litres per minute with the 5 bar supply. In this example, the standby on delay time has been set to 5 seconds. The standby pressure has been set to 2 bar. The display shows current pressure, flow rate, temperature and accumulated flow values, all of which can be monitored remotely. We will now simulate that the machine production has stopped by stopping the actuator, resulting in a reduced flow rate. In this demonstration, the standby signal mentioned earlier is provided at the same time as whenever the actuator is instructed to stop. Once the flow rate drops below the predetermined threshold, the standby timer is started. Once the timer has expired, the air management system reduces the pressure to standby setting. The display text changes colour from red to green, indicating that the air management system is now in an energy saving mode. You can see the flow has dropped from what was approximately 80 litres a minute to 40 litres per minute, with the reduced supply pressure. If the machine remains in standby mode for a period of time, in this example 10 seconds, and if required, the air management system will change to isolation mode and close the residual pressure relief valve, stopping the supply of air and exhausting the machine. When the machine is ready to start production again, it switches off the standby signal and the pressure will now increase back to 5 bar. In this demonstration, the standby signal is removed at the same time the actuator is instructed to start. This concludes the introduction to the air management system and its energy saving functions.